All right. All right, well, thank you for the introduction. As you just found out, my name is Scott Stender. I'm a partner with ISEC Partners. We're a security consultancy, and I work primarily in our application security consulting. I'm here to talk about attacking internationalized software. So why listen to this talk? Well, first of all, let me thank you for being at this talk, because the title doesn't exactly scream written by a marketer. It is something that is a very kind of corner case type of thing in terms of software development, just like security once was, but together, security and internationalization don't tend to play very well. So this talk is about being able to use or misuse internationalization against the ends of the system designer. It is something that there's a great deal of research potential. I found a number of vulnerabilities that were based on the techniques I'm talking about here today, but I acknowledge there's plenty more out there to be found and plenty more systems that have yet to be looked at all. So I think it is something that I hope other people will pick up, take a little bit more look at. And for platforms, internationalization is a cross-platform concern. Many of the demos in this talk will use Windows as an example, but don't think that it's just a Windows-only concern or just an application-specific concern, the ones I demonstrate. It really is something that hits almost every application developer. All right. So let's launch into the basics. Internationalization. So internationalization is whatever you have to do as a developer to write your application once and have it run against a number of locales. A locale would be a cultural specific set of preferences. So things like how do we represent the code page or the characters that we want to talk in, and how, what sort order do we use when we sort text, and how do we represent timestamps and currency and a number of other things. And if you properly internationalize your software, you have to write it once, and then you can run it on English, you can run it on Japanese, you can run it on German, you can do it anywhere. And it'll just work flawlessly and in a culturally appropriate way. Within all of those areas, most of this talk will focus on character manipulation, and there's a good reason for that. From a security perspective, a lot of times what we're going after is data, and that is where representing data comes into account, and so that's why character manipulation, being able to manipulate that data in ways that's unexpected, is really the core, portion of this talk, but there are other areas of internationalization I'll talk about later that sometimes can result in security failures. So with internationalization in code pages, there are plenty of code pages. You have single byte code pages. A lot of us are familiar with, a lot of us in the United States are familiar with, the one big single byte code page, ASCII, which actually, if you're to be pedantic about it, it's a 7-bit encoding scheme, and a lot of times people just happen to put it into a full byte because computers can chomp on it well. There are a number of other single byte character pages out there, all standardized by the ISO and whatnot. There's also a number of multi-byte character schemes. And these are, again, code pages. Multi-byte code pages are ones that will represent a character based on one or more bytes, depending on how the format is determined. And examples of this are a lot of the older ANSI, Japanese, Chinese, Korean things. Things that require a lot more space in their encoding space to represent characters than a single byte would allow. And then, of course, there's Unicode, which we'll talk about in a little bit. Now, once you get everything assigned to a code page, or more specifically, once you get all of your semantic data assigned to code points inside of a code page, you have to encode it. All a code page is just a mapping of A equals this point. But encoding that is something that is completely independent. And within encodings, ASCII is an encoding of that code page. It's a pretty simple one-to-one mapping. But UTF-8 and UTF-16 and UCS2 and UTF-32 are all different encodings that represent the same code points, and they are interesting to look at the differences between them. If you look at a lot of them, they look nothing like one another, even though they represent the same data. So that's one distinction we want to keep in mind, is encodings versus code points. So Unicode, one code page to rule them all. The idea of Unicode is to have a single code page that represents all the world's data. We're talking about today's data, whether it's English, German, or Japanese, or Chinese, or everything that's in Chinese, and everything that's dead. There are portions of the Unicode code planes that are dedicated to Sanskrit. Right? And this is something that people are trying to have a single way. We'll never have to deal with any of this anymore. As long as we put everything into Unicode and encode it properly, life will be good. So that's the idea. And there are many encodings available. I mentioned a few already. UTF-32, UTF-16, UCS2, UTF-8, UTF-7 are just some of the ones you see right away. Unicode is a 21-bit encoding scheme. Now, a lot of people, when they think Unicode, they think of 16-bit characters. Well, those 16-bit characters are called the base multilingual plane. They are the very basic set of characters that most people will be able to communicate in. So things like English and European languages and Japanese, or most of Japanese and Chinese. But there are, for people who need to expand beyond the simple 65,000 characters that the base multilingual plane can encode, can go into the upper planes. And that's where things like Sanskrit and lesser used things are. Now, all the encoding schemes that we have are going to try to encode as much as possible. And if you're talking about UTF-32, UTF-16, or UTF-8, or UTF-7, they can encode all 21 bits. UCS2 is simply using, is simply the 16-bit code point that can only encode the base multilingual plane. Now, a lot of people think UTF-16 and UCS2 are the same thing. The one thing about UTF-16, and if you're using Windows, and the basic character type is a 16-bit character, WCAR. If you're using one of those, you're using UTF-16, and you actually can have a multi-byte character with that. And that's called the surrogate pairs. You have Unicode D800 to DBFF and DC00 to DFFFF, or FFF. Those are going to be what are called lead bytes, and this is something that we're going to go over here in a moment. But you can encode the full 21-bit character set in UCS16 or UTF-16 using those lead bytes. Now, what's a lead byte? I've thrown this out a couple times and haven't explained it very well. A lead byte is a very simple way of expanding your encoding space without breaking lead byte, backwards compatibility. So when we tried to move beyond ASCII, we had a single byte 8-bit character or 7-bit character that we wanted to be able to use with broader encoding schemes. So a lot of these encoding schemes are ASCII compatible. That means if you are going to encode the lower 128 characters in ASCII, it should be byte for byte compatible more or less. But if you want to do more, then what you do is you have a lead byte that says, I'm not a character, me and the guy after me are a character, or 2 after me, or 5 after me, in the case of UTF-8. And here's how that works. This is an example from a Japanese code page, sometimes called ShiftGIS, or in Windows, it's Windows 932. And with that, you have a lead byte and trail byte. On the lead byte, you'll see on the left is just a simple 0 through FFF, or 00 through FFFF. And you'll see that some of them are white, some of them are gray, some of them are dark gray, and some of them are blank. Now, the white characters on the left are things that are a single byte character. So if I want to encode A, which is hexadecimal 41, in this code page, I just say hexadecimal 41. Now, if I want to encode Unicode 2032, which is a code point, if I want to encode that in this page here, or in this encoding, then I change it to, you'll see that it's the first byte, the lead byte is hex 81. The trail byte, if you look over there on the 8th row in the C column is there. There's our 2032 prime character. And so together, the lead and trail byte would be 818C. So if I was a parser that was wanting to understand the ShiftGIS code page, say I was converting to Unicode, I'd go through different bytes and I'd say, okay, I'm on hex 41, this is an A. I'm just going to encode it to Unicode A, 41. If I'm going through and I see lead byte 81, I say, hey, this isn't a character, this is a lead byte. I check out what's next, and then the 2 of them I use to look up and see what is the actual character, which is Unicode 2032. So what would come out there be 0041, 00, if we were doing another on the UTF-16 thing, UTF-16 code page would be 0041, 2032. So that's how lead bytes and conversion kind of work. Any code page that relies on multiple bytes, whether it's the ANSI code pages like ShiftGIS, or if it's UTF-8, rely on this notion of I'm a lead byte, and the person after me affects the actual code point that's coming out. And we will see how that can be used for malicious purposes a little bit later. Any questions so far? All right, feel free to jump in anytime. So almost every platform has support for internationalization, especially Unicode. Results depend on the Unicode standard supported by the platform. For example, platforms can be defined as platform support by Linux system programming and Windows system programming. There's also the higher level platforms, .NET and Java, or even your programming language. All these things have various level of Unicode support, and and how much you can encode in them and what kind of attacks are going to be very specific to what they support. Now, if you use one of the newer ones, .NET and Java, that wasn't around when it had to worry about using ASCII versus the Latin code page versus Latin 2 versus Japanese versus Chinese. They usually don't worry about it so much. They'll support Unicode and maybe another lesser encoding and call it quits. Now that's nice because you have less variation, less attack surface, less things to go wrong. So you could say, hey, great, best practice. All I got to do is use .NET or Java or something that's been around or created rather recently, and I'm all safe on my internationalization attacks. And that's not so much the case, because even though your application may try to keep things in one understood canonical format, you are always talking to things you don't control. You're talking to your web server, you're talking to a client, you're talking to your backend web service, you're talking to your backend database. All these things are, have a internationalization boundary and therefore attack surface associated with them. So to use a couple of platform examples, and this is just 2 samples, in Windows is built with Unicode at its core. Most native API functions take UTF-16 strings. Now, for example, I dare you to try to find the exported function create file. Just create file, for those of you who are familiar with Windows programming. There isn't one, because it is per compile defined to be either create file W or create file A. If you go with and that would be wide string versus old ANSI one. And if you use one of the old ANSI ones, then it will convert to wide car before sending it down to the actual syscall. So everything eventually gets converted to Unicode in Windows, or almost everything. I guess you could, if you don't do a syscall, you can stay all in ASCII or ANSI or whatever you want. But there's always going to be a Unicode conversion attack surface in Windows. Broad generalized support through OS and applications. Because it's so integral, and because Windows has been designed from the ground up of late anyway to be Unicode compliant, there are always some free things you get for internationalization with programming in Windows. If you use a WCAR type, and if you use the core libraries, you're just going to be able to work across different locales, and it's not going to be very difficult. Now, that's why they serve as an example, as the example for today's demos, because it does have such core support, but at the same time, everything isn't the same. If you install an English build of Windows, it's not going to have support for all the code pages and locales than the Japanese build of Windows does. And so it's something you have to keep in mind when you're testing for nationalization. You can't just test on an English machine and think that you're safe. You have to test across different builds. And character cassette conversion in Windows has 2 core APIs, which I'll put out as examples here. These are things that are Windows specific, but the general ideas translate pretty well across any kind of conversion. Multi-byte to wide car. Now this is what converts from the locale-specific code pages, ANSI or ISO or whatever, into Unicode. A couple things to take note. There's the code page that you specify. So what am I today? I am Windows 1252 and I want to become Unicode. Well, there are a couple things to keep in mind there. Couple of the parameters also point out are the source and destination strings. You have count of bytes, count of characters. If you mess those up, you're going to get a buffer overflow, and that's something that's been a historical problem. Going the opposite direction, going from all of Unicode down to a locale-specific string, is carried out by wide car to multi-byte. Now, this is one interesting area to point out here is that in the DW flags parameter, you have this thing called WC no best fit chars. Now that means that in general, if you're converting from a many to one relationship, you can have many things that are kind of like an apostrophe. You have your standard hexadecimal 27 ASCII apostrophe, but you also have in Unicode the properly curled apostrophes that you put before and after a word. And you have prime characters, and you have other marks and things that look like apostrophes. And if you want to have, after the conversion, have it still resemble an apostrophe, the conversion can cut you a break. It'll become an apostrophe, a hex 27 apostrophe when it gets down to the locale-specific string. Or you can say, don't best fit. If it doesn't fit, make it the default failure character, which is by default question mark. So a couple of things to take away from both of these is you're always going to be converting between a locale-specific string to Unicode, which is going to be almost always there's going to be one locale-specific string which matches directly to one Unicode character. I'm sorry, character to character. Going in the reverse, you're going to have a many to one, where there's going to be many things that can best fit into a specific one. Any questions about that? All right, the good stuff is coming soon, I promise you. Question up front.
Can you say a couple of words about multi-byte structure? Could you mention it as 1 byte symbol?
I'm sorry, I don't quite understand.
I'm just a little confused. Originally we have 1 byte that we use ASCII.
Yeah.
And then it was started using multi-byte before going to Unicode. Why multi-byte were necessary?
I think because, and this would be an exercise for the historians rather than the engineers, But I would say probably because Unicode was something that required a dedicated standardization effort. It was something that took a while to get going. It's much easier from if I got to get more characters in there to just put that multi-byte character in, set in there to have that work. I mean, it was something that was quick and dirty and allowed for you to expand your encoding space. But it wasn't something that was designed to be used across all languages, across all platforms for the rest of time. Any more? All right. So in the Linux, Unix, every Nix world, general assumptions are a little bit harder to make. There are a couple of standardization efforts, and obviously the POSIX locale offers some standardization. A lot of times you'll see that there'll be support for core UTF-8 by default on many of the distros. It's not something where you're going to be able to make as many set statements like everything will become UTF-16 when it gets down to the system layer, because it is going to be very configuration specific. And the effect of that is it really pushes internationalization up the stack. If the platform doesn't act as, if the platform doesn't act with the same by default behavior, then the application developers are going to have to do more to integrate internationalization in, and that's going to be something that's going to make things very, application specific. So, for example, if you go to a lot of the internationalization support websites for Linux, you're going to see things on, here's how I can use a shell that will by default support Japanese characters, or here's how I can use an editor that supports by default this code page. And that's something that's going to be, when you're attacking these systems, you really have to understand a lot more about the application you're attacking because it is going to be specific. This is good and bad because without the pixie dust internationalization happens approach, if you have internationalization in your application, you pretty much really want it to be there. You must know what you're doing, or that might be a stretch, but you must know that there's something to be done and you're integrating a library or something that has internationalization support. Then again, anytime you explicitly do something like that, it's complicated, it's error-prone, often implemented insecurely. You have a lot of flaws. There are common utilities and libraries that offer support, like International Components for Unicode is an open source library that does all the conversions along the same lines as what we saw with multi-byte to WideCar and the reverse. IconV is a utility you'll find in most distros that will convert files between different encodings. libiconv is the same thing, but in a library form. And you can always roll your own because everybody else does, and please don't. And there's a couple websites you can check out if you want a bit more information on standardized internationalization concerns in the StarNix world. But everything else, support isn't just from the OS. Like I said before, it depends on the programming language you're using, or virtual machines. If I'm using Python, what I have to do to get a Unicode character in there is very different than what I have to do in Windows, or if I'm programming in C++ for Windows. And again, very different than what I'm using in .NET. Virtual machines, like those used with .NET and with Java, will also add another layer of core nationalization support where things have their own unique representation and inside memory. And then you also have application-specific things, something that doesn't care what the OS or virtual machine provides, but it tries to make its own UTF-8 parser in there. So it is something that, even though there are varying levels of support from different platforms and libraries, it is something that you're going to hit in almost every application. And this offers a unique attack surface. We're talking about things that are based on standards. This is cross-OS or language, application class, implementation. If you're using HTTP, you have internationalization support, whether you know it or not. And so this really does hit almost every application out there. So for example, if I'm writing any application, my development platform is going to have some sort of internationalization support. My external libraries, anything I call into, same thing. Operating system, same thing. Application server, database server. Anytime I'm going off a machine, I'm going to have almost certainly some kind of attack surface or crossing an internationalization boundary. And of course, the client's at the end of the line. So with web applications, you have code page that can be set on every HTTP request, response, and in the header of the HTTP page. And there's 3 unique attack surfaces where I can start putting mismatched encodings or double encoding to get past things. A code page is set on the first line of every XML document. So if I'm talking over a web service to an HTTP server, I have the XML document, the HTTP request encoding, and everything coming back is different areas where I can perhaps specify a code page is other than what it's expected. With the old multi-byte to WideCar things, a lot of conversions will depend on your default code page, and that's what the CP/ACP stands for. So when you test these things, you really have to change your system and user locales and try testing on something that's a built up from scratch Japanese machine with Japanese databases and everything else, because you'll be surprised at how things behave differently when they act off of those different defaults. So if we're talking about a standard stack of a web service, you have an HTTP parser sitting on top of an XML parser in SOAP stack, sitting on top of your application logic. And this is where most people are writing their applications. You take in your data that's coming from the web service and you're sending it out to a database. That's usually the most practical point for people to control their input validation and check for internationalization issues. But even below that, you have your database access library. You have your ODBC and whatnot. You have your database, SQL Server. You have your operating system down there. Anywhere along the line, if somebody makes a mistake and allows manipulated data to pass through, then you have a potential issue. All right, and we'll see a couple of those in a moment. So that was the background. I tried to keep it quick, but if anybody has any questions, feel free to ask now. We'll get into some attacks in a moment. All right, must have nailed it. Historical attacks. Now, anytime somebody's asked me about my talk in the last few weeks, they've always said, so, like that NT4IAS thing. Internationalization has received some attention from the security community, and there have been public flaws along these lines. You can pretty much chalk these up as lessons learned. We saw those two APIs before, messing those up, the count of bytes versus count of characters, whether it's a 1 byte per character or 2 bytes per character. All that resulted in a bunch of buffer overflows, input validation, standard application attacks. And people, for the most part, now know that you have to use these APIs with a lot of diligence in order to prevent such attacks. It's in writing secure code and everything else that does that sort of thing, or that gives guidance and that sort of thing. Another thing interesting about, though, is that a lot of these behavior, in Windows at least, there's a lot of functions that depend on your compile time flag. So for example, if I use a tcar type, or if I use an elster star function, then these things will act differently whether you define with the Unicode flag or not. So you might test your application to death and find that there are no flaws when it's compiled without the Unicode specifier, but then when you do, you find buffer overflows all over the place. This isn't something as much of a concern if you're releasing a binary and send it out to the world, but if you're releasing open source software, you have to realize that that could be a change and test it twice. The big one, though, that everybody refers to is the non-minimal UTF-8 encodings in NT4IAS. So, abstracted, web server is just a thing that takes a request from the web, converts whatever was requested into a file name, opens the file, sends it back to the user. So typically I'll see, HTTP, web server, scott.com, and then go to my web folder and index.html. And people would look at that and say, hey, well, I want to get something outside of the web root, and I don't want to have, the index.html. I want to be able to pull down somebody's SAM or password file. So they say, okay, well, I'll just ask for the web root, // whatever, one of those two things. Now, most people who are creating web servers realize that that's an issue, so they check for things like //. So here's where encoding comes in. I encode it as %2e, %2e, %2f, which that is the hexadecimal representation for period, /. If somebody were validating and looking for it specifically for // then that would get by it. If it were to be decoded later on, then it would go into the open file command, create file, whatever, and serve up the malicious file. So people thought, oh, even that, I'll decode it. I'll look for %2e, %2e, %2f. And then here's where the flaw happened. Same thing, but I say, instead of %2e, I say %C0AE. Now that's a UTF-8 encoding, which is of the same character, %2e, but UTF-8 can be between 1 and 5 bytes long. So instead of using the shortest representation, which is %2e, they used %C0, %AE. And this was something that the decoder did not check for, and so this allowed you to request any arbitrary file off of the disk with the web root. This is something that was fixed years ago, and the Unicode Standards Committee said that if anybody else does this, then they cannot advertise themselves as Unicode compliant. So if your by default UTF-8 parser allows non-minimal encodings, you can't advertise yourself as being compliant. People lose money, so almost nobody does this anymore. Now what they do instead is going to be the subject of one of our attacks here in a moment. Any questions about these old attacks? Oh, that's outside. Okay, current attacks. So with the current attacks, your validation is performed on your input and then changed to locale-specific text. So I'm reading in a Unicode string. This happens a lot in the standard newer platforms. So I'm a web app developer, I'm using .NET or Java. I'm almost always going to get a post parameter or a query string parameter as a Unicode string. So when I do this, when I read that in, I then convert it to something that's locale specific, like Windows 1252 or ISO 8859-1. When it has that conversion, it's a many-to-one relationship like we talked about before. So we can have that apostrophe character, the apostrophe-like character, become an actual apostrophe. And here's one example. The Unicode code point 2032 is the prime character. So the prime character is very similar to an apostrophe character in look, but obviously not in semantics, and it has a lot of concerns within database applications. When it's converted to Latin 1252, without any kind of, don't best fit me, at least on Windows, it becomes hex 27, the actual apostrophe. Same thing happens with quotation marks, numbers, letters, etc. There's a number of things that are equivalent characters to apostrophe if you allow the conversion routine to give you a break. And Latin 1 isn't the only code page. Have you tried your Japanese web client lately? This is a really big concern for cross-site scripting attacks, where you can put up a bracket-like character, bracket script, but instead of an actual bracket that people tend to filter out, you put in something like it. It's interpreted by a Japanese client properly, but not by an English one. So let's take a little time for a quick demo. Anybody have any questions while I'm getting that ready? Okay. So here is a very simple web service in .NET called SQL Demo. It allows you to interact with it over this form here. It has 4 simple routines: log in user, log off user, print info, and update my information. We're really only going to mess with log on user here. And you'll see that let's see, can you guys see that all right? There we go. So it takes a very simple login. If I say my name is Stender, my password is Scott, and I invoke it, very strong passwords, I get a valid cookie back, which is 1,000. If I give it the wrong password, like Scott period, then I get -1 invalid cookie back. So now I figured this logon user, like every other web application, probably has a database back in there with a users table, or does select star from users where name equals and password equals. So I'm really smart and I type in an apostrophe. And I type that, and I get -1. Okay, so maybe not. However, we saw just a moment ago that Unicode code point 2032 is a somewhat equivalent character to apostrophes if you allow that conversion to happen. And so perhaps this service does a round trip, put things down into Windows 1252 or 8859-1 or something else where it might become an apostrophe. And it so happens, this right here, that is unprintable, is Unicode 2032. You can see it looks a little bit like an apostrophe, but it is not one. And if I type enter, then I get unclosed quotation mark. So again, we saw a moment ago that when I typed a simple apostrophe, the standard SQL injection test, we got nothing. But when we type in something that's similar, it got best fitted to an apostrophe, sent to the database, and now we have a pretty standard SQL injection exception occurring. So just to show you guys I'm not lying here, there is somebody named root in there, and if I say root, funky character, hyphen, hyphen, and we get a valid cookie back, and if we were to go say print info on that person, it was 1001, I believe, then yes, indeed, my concocted application says that it's root. Now the application does one really stupid thing, just for demo purposes. When it takes the Unicode string, it explicitly converts it to Windows 1252 using the default .NET application encoding mechanism. And you can see I have put a big comment there that says dumb. Now the one thing is you'd say, who would possibly do this? Well, nobody will possibly do this in this one very limited example, but you will see this when it crosses machine boundaries. Let's say this wasn't my local database that was on my machine that was built to run with the application server, built to run with .NET. And let's say it's some other, MySQL server. It's on another machine. The machine is running a different locale, and it has to do some sort of conversion in order to make that work. You're going to see things like that. I have seen things like that. I wish I could have demoed them, but can't. Any questions about the foundation of that attack? Under what circumstances it can occur? Okay. I'm sorry, I can barely hear you back there. Oh, well, for demo purposes, I didn't want to start pulling out raw HP posters. What you could do is if you were using WebScarab or any other web proxy, or if you're just typing things in a netcat, you could just simply encode the UTF-8 encoding of it, which I forgot off the top of my head, but you basically convert Unicode 2032 to UTF-8, put percents before it, and then send it off. I actually have a tool and a demo in a little bit here that does that. For this particular demo here, the way I got that character was to just open up the car map and say go to 2032 and copy and paste it. All right. So that's the big attack pattern you see when you're starting in Unicode and you're going to a locale-specific text. There are other attack patterns in the reverse direction. So I get something that's locale-specific, I convert to Unicode, and then I do something interesting with it, like access a database. The attack pattern here is eating characters. So we talked about UTF-8 and shift-gist that have these lead bytes in them. And these lead bytes don't mean anything of them by themselves, but any parser is going to interpret them in the context of what runs after it. So if I send somebody a character like, well, to go back to the shift-gist example, if we were to look at, if parsers look at hex 8260, then they were to do that, look up through the code pages that I illustrated earlier, that would be equivalent to the Unicode code point FF21, which is the full width Latin capital letter A. So there's another funky character that corresponds to something in the alphabet that might be misused by people. There's plenty more like that, but that is how the lead byte and everything occurs there. Now, if I say 8227, that's not mapped to anything. If I were to go back and look through those code pages, I'd see, okay, hey, here's the trail byte page for lead byte 82, and I look, and 27 would be unmapped. So that, when you'd convert it, would become error. It would usually become whatever the default character is, and that's going to be like a question mark. If I put in hex 822727, nothing with an apostrophe, that will become, so like I said, that'll convert from 8227, will become unmapped, become question mark, and it'll be followed up with a 27. So where is this interesting? Well, let's say when I get my locale-specific text, I perform validation on there. I look for apostrophes. I go through and say, okay, here's 8227. Oh, there's an apostrophe. Double it up, 8222 or 822727, and then I send it on back to the database routine, which encodes it into Unicode and then access to the database. Then all of a sudden I become, whatever it was becomes blah question mark, which is the 8227, and then the apostrophe that was put in there to double up, and then it goes on from there. Now this is one example from shift-gist. You could do the same thing with anything that stupidly eats characters within the parser. If I were to put C027 and something said, hey, this is UTF-8 lead byte and then the trail byte, and I go through and I escape out the 27 and then the C027 comes out, same thing would happen. This is particularly devastating against anything that escapes or doubles up characters in order to make them clean. Any questions about that? All right, well, I don't have a demo on that one. The next one is foiling canonicalization. So a few minutes ago, we talked about how UTF-8 had non-minimal encodings that were explicitly banned by the Unicode Standards Committee as being not compliant if you do it. And the example we gave was C0AE, which is a non-minimal encoding for hex 2E, which is the period. Now, that left all the system implementers to decide what do we do when we come across one of these. And what most people do, actually without exception the ones I've looked at, is they simply drop the character. Well, why do you drop the character? Well, sending up an error every time you have a converted character go wrong is going to cause all kinds of problems. It's something that you don't want to throw an exception up or every database in the world will die. I mean, it's something where you pretty much have to detect and fix it. So in order to have something, still work, they just simply drop the character. And so where is this interesting? Well, if you're foiling canonicalization once again, go back into the website example. We have the web folder / index.html. We can't get by on .. to kick us out. But then we do non-minimal encoding, .. non-minimal encoding, .. blah. Now, if something looks at that and is looking explicitly for .. or anything along those lines, they're going to kick it out. But they're going to see here not there. And so they're going to allow it to keep going. Now, when that gets converted by the UTF-8 parser, it's going to be dropped. And so what comes out the other end? .. And then a demo that shows this happens but doesn't have any specific security issue is to log in. Now, for those of you that are really up close or have very good eyes, There is a way to use this application which is based on get parameters, and I wish I had a bigger font here, but I have to do encodings which are escaped out by the form submission method. But anyway, if I click on this, it's the same login user, sends in my name and password, and I get the same success string. So my password is here at the end, it's still $COTT, but if I put in %C0, %AE, then that should be a period or a non-minimal period or something, a question mark inside the middle of my password. This should kick it out. Oops, and it did. Had a typo in there. Oh, thanks. Okay, so there we go. %C0, %AE in the middle of Scott, and that comes back valid. It dropped the non-minimal encoding, still let everything go through, and this would be of extreme interest in trying to bypass any canonicalization protections. Any questions? I left more time for, whoops. So a third attack pattern, I'm sorry I don't have a demo for this one either, but it's mistaken identity. Now many of the code pages that have been designed, this goes to your question a moment ago, many of the code pages have been designed to be ASCII compatible. So that if I have a single byte that is from the old alphabet, it kind of looks like what we are used to. An A still looks like hex 41, or maybe 0 extended hex 41, like in UTF-16. And a lot of validators have taken this advantage of this of this similarity. So if I'm, creating a validator that's looking for cross-site scripting, I can just go through and look for, hex 00, 3E script, hex 003F or whatever it is. That's a very useful thing. But there are other encodings for Unicode that we talked about that aren't ASCII compatible, like UTF-7. It actually is ASCII compatible, but it doesn't have to be. Basically, it's a 7-bit encoding scheme designed for, things like mail transfer. And what you can do with it is, if it's an A, you can still put an A, but if it gets outside of the known safe characters, you're supposed to base 64 encode it, more or less modify, and add a plus and minus on the end of each one. Now, there's nothing that says you can't do the same thing with a script tag or an apostrophe or anything else that's deemed safe. And actually, this was a flaw that hit Google with the cross-site scripting not too long ago, where he took a script tag, UTF-7, sent it up there. The validating routine just saw a bunch of standard characters, A, B, C, whatever. Didn't think that it was anything malicious, so let it pass on through. When it got back over to the browser recognized that it was UTF-7, decoded it, and displayed it. Recently on BugTrack, there's been a lot of discussion about what 7-bit ASCII should be interpreted as. ASCII is a 7-bit encoding scheme. Computers don't chomp on 7 bits, they chomp on 8, at least. And so what happens to that, the most significant bit? Well, ideally, you should ignore it. A lot of people just simply 0 extend it. It becomes, hex 00 through hex 7F. But ideally, by the standard, that top bit doesn't matter. So you can simply put a bit on there. Hex 27 becomes hex 87 or A7. And if you put that in there and it actually interprets it as proper ASCII, it will become apostrophe and go through to your database, or same thing with script tags or anything else. Other things like that, EBC DIC doesn't look like it. UTF-7 and ASCII are the other two big ones. Any questions about that? All right. So here's the bonus. So we talked a whole lot about character encodings. At a basic level, that's where most of the data is. But we talked earlier about how internationalization includes a lot of things, or locale-specific preferences, timestamps, and sort orders, and currency symbols, dollar versus euro, and all that other good stuff. So the timestamp attack, today is August the 2nd, 2006. So if I have a timestamp of 08/02/06, that could be August 2nd, 2006, or February 6th, 2008, depending on how you interpret that string. So if you have a ticket expiration, which is persisted into a string rather than a computer time, and you send that across machines, very interested in like brokered authentication schemes, and that machine is of a different locale and interprets that string differently, then all of a sudden you have a ticket expiration that occurs 2 years in the future, not right now. Sorting attacks, this one's kind of interesting. So which comes first in general, Apple or Aardvark? Aardvark has 2 A's, so it'll come before Apple. If you go in Dutch, AA is a lowercase version of a character that's far later in the alphabet, so it actually comes pretty close to the end of the alphabet. So if you're building a sorted list for integrity checking or something along those lines, then and you interpret that on Dutch, it's going to be pretty bad. Same thing with what is your proper decimal separator? You know, sometimes it's period, sometimes in other locales it's going to be a comma. If you persist your data into a CSV format, then your bank is going to be very unhappy when all of a sudden you can manipulate that format. So there's a couple of other things to think about, though character encoding is typically the attack that is most worthwhile. So in support of all this, are any questions along those lines? Okay. Yep.
So in all those Unicode pages, do the Unicode pages themselves say what the proper order of characters are as they're stored?
Yeah.
Can I look up in the, I mean, Dutch is represented in ISO, right?
Mm-hmm. Yeah, so there's Unicode specified sort orders and locale specific stuff like that, and same thing with the different ANSI code pages. Anything that's...
If you have a sort function that understands Unicode, then it should go like that.
Mm-hmm.
You can audit for text. That's maybe just the text that you recommend.
Yeah, definitely. So you know, testing all these equivalent characters, eating characters, things like that is very difficult. And so I've recently written a tool that has taken right now a bunch of equivalent characters to core ASCII characters, which usually cause problems. Things like apostrophes, quotation marks, brackets, parentheses, and we'll then take an arbitrary HTTP post or GET, manipulate all the parameters, and see if it can find issues, kind of like the one we discussed earlier. Call it I-18 in attack, which is, I-18N is air nationalization shorthand. And I'll give you a quick demo of it right now. So the way it works is it takes, it'll look for properly formatted HTTP requests inside of a general folder. You can use it with WebScarab. You know how WebScarab will persist all of your HTTP requests, put it in a single folder. You can just point at that, go through and read those requests, and then identify the parameters, and then start working against them on with a XML database of potentially nasty equivalent characters. Right now I have it set to try out apostrophe and quotation mark. So I run that, processes my 4 requests, and it comes up with a little HTML output that describes what it found. So this was testing the system that we were looking at earlier, the one where if you typed in apostrophe, it would validate that and kick it out. But if you're testing with something that is an apostrophe equivalent, it would hit issues. So you can see it starts off with apostrophe, trying a few different requests. Then it goes into CAB9, which is the UTF-8 encoding for one of the things. So the person who asked that earlier, there's the UTF-8 encoding for a lot of these equivalent nasty ones. You'll see that there is an error detected. And if we look at the response, we can see within there that there is incorrect syntax near test, unclosed quotation mark before character string. So this is something that will quickly and easily try a number of different characters. You'll see that it's not only CAB9, CABC, CB88, and then a couple of other ones. All of which are going to be Unicode equivalents of apostrophe that when converted to Windows 1252, which is the default code page in English builds of Windows, will become apostrophes and be potentially used for this. The test system that we had specifically did a round trip to Windows 1252 to show this. Same thing would occur if you had if you're round tripping to ShiftGIS or ISO 8859-1. All these things have their own unique set of Unicode equivalents, and this tries to catch all of them. And so it goes down. You can see a couple more come in there. So there's a quick automated test of these sort of things. Any questions about the tool and how it works? Okay. So then oh, did I hear one? Right now, you can email me. There's my, it is not quite ready. I was hoping to have it ready for release at Black Hat, but there are still a couple of rough edges around it. But you can go to our webpage at isecpartners.com or email me here, and I'd be happy to give you either pre-release or final release versions. The big takeaway of all this discussion is that internationalization is a hard thing to get right, and a lot of people and a lot of effort has gone into trying to unify things and make it very simple. With regards to the Unicode standard, I'm not saying by any means don't use Unicode. Actually, try to use it and stick with it and validate according to it. I've seen a lot of validation routines that try to take into account, hey, let every punctuation go through, and then try to get rid of and then try to get rid of specifically nasty characters. And this is something that the security industry for years has said is a bad thing. Always find the known safe data, and try not to cleanse and identify blacklist data. This is a very good reason why that is the case. If anybody ever pushes back on you, this is always a good reason to, a good presentation to cite of, hey, here's a bunch of different ways you can get past, simply blacklist and cleanse data validation routines. From a defense point of view, one should always do is try to get in Unicode, stay in Unicode, and don't convert otherwise. With my test system here, I do explicitly round trip to 1252 in order to identify. I had to explicitly round trip in order to get something to go wrong, and this is something, and it was simulating what would happen if it were to go off-site or get persisted into another format. But if I hadn't done that, then my very simple, application server, database server, sending out data would have been more resilient to attack. Now, from an attack perspective, certainly understanding that checking apostrophe and hoping that it hits, and if it doesn't, then going on is not going to be sufficient. Really looking at some of the equivalent characters is going to be what is required for a more comprehensive test, and hopefully we'll have some help for you on that in a moment. So this talk went a little bit quicker. I was expecting more questions, but you guys have been a great audience. So go ahead.
Regarding the UTF-8 parsers that drop non-minimal encoding, do you think there's a better way to handle that? Like doing something else with those bytes, or bytes a better idea? Or do you just only check, for example, file path validity after you're sure all the encoding were loaded? Is there a better behavior for the UTF parsers? And you should only check for file path validity after UTF parsers has been.
Well, the question was with regards to the UTF-8 parsers, is there a better way to handle them than to simply drop the character? And from if you're the application developer relying on somebody's library, the only thing you can do, and the best thing you do, is to always validate your data at the lowest portion of the stack that you can. So don't wait till you decode from Unicode or from UTF-8 to Unicode to check that. So that's the one thing. As far as what the core library designers would do, there really isn't something that one could say is always better. I mean, as a paranoid security guy, I'd be happy if they'd throw an exception or die or do anything else, but cause issues. But the reason why I think that they've chosen this path is simply because it is a compatibility issue. There are many systems out there that are probably using non-minimal encodings for whatever reason, and to have every database in the world die because Windows changed their default handling for UTF-8 or Linux changed or whatever would probably not have been a very easy pill to take. And every application that relied on that would have to be rewritten. So the big thing to do is just validate your input as close to the bottom of the stack as possible. Any more? Question in the back. I'm sorry, what was that again? You mean if you are running the application on the server, or if you are remote? If you're remote, I'm sure that there are fingerprinting techniques out there, but for the most part, you don't really have to do a lot of detecting. You can often guess. I mean, there's always going to be a set of core supported code pages that are going to allow plenty of attack surface. I mean, UTF-8, all the ISO code pages. If it's a Windows machine, all the Windows code pages, and even a lot of times Linux machines will support those. So a lot of times those will give you enough that if you have the ability to explicitly say what code page you want to be interpreted as, that's enough attack surface. I mean, other than that, that's where the tool comes in, where you're trying to send everything that could possibly go wrong to the system and seeing what it chokes on. If you looked at the output from that tool carefully, you'd notice that there are a lot of things that did not hit errors. Those were just character points that were interpreted as apostrophe on different code pages, and so they were handled appropriately. Of the what's coming back, you mean? Oh, of what I'm sending up. Yeah, if it's a post parameter, if it's a post request, then you can specify in the content type HTTP header the specific encoding you want to be interpreted as. And so at that point, you can specify anything that the server would potentially have. And so the one right there just hard-coded to UTF-8 because I was looking for Unicode to locale-specific code page conversion issues. But And one of the things that has yet to be implemented is the eating characters attacks. One of the reasons why I didn't release it today. And that would be something where you would specifically say, my username equals, hex 82, and leave it at that. That would be just a lead byte by itself. And my code page is shift.gis. And then having that go up to the server and perhaps eating a trailing apostrophe or something else like that in a SQL statement. Now, getting it back, that's going to be server specific. A lot of things will default to UTF-8 on what they're sending back, but that's not always going to be the case. Anything else? All right, well, if you have any follow-up questions, feel free to email me. There's my email there. I have a couple cards and some CDs that we have all of ISEC's talks on. Be happy to answer any questions offline. Thank you.